Is the mean heart rate of Singaporeans with high cholesterol level higher than Singaporeans with normal cholesterol level? Descriptive statistics. Our research question. Is the mean heart rate of Singaporeans with high cholesterol level higher than Singaporeans with normal cholesterol level? Our research question establishes a cause and effect relationship between cholesterol levels and mean heart rate. Our independent variable is cholesterol level. The two groups we have is high cholesterol and normal cholesterol. Our dependent variable is heart rate. We feel that this is of interest because we want to research and find out whether the cholesterol levels of people would affect an individual's ability to pump blood to the rest of the body, in which may ultimately affect their health. This is also of interest to us as this question relates to our course, our specialization, and what we are learning. The heart rate of people can determine many things, as the heart muscle is responsible for supplying the body with the blood and oxygen it needs. Cholesterol level is one of the main factors in causing heart diseases aside from smoking, high blood pressure, and diabetes. In our research question, we use the word higher than because cholesterol levels affect heart rate. For an individual that has high cholesterol, his heart rate is most likely to be higher than an individual that has normal cholesterol level. This is due to the buildup of cholesterol in the walls of your arteries, narrowing it and causing blood flow to the heart muscle to be slowed down or blocked.
Below is a summary statistic for both high cholesterol and normal cholesterol. The summary statistic consists of the minimum, lower quartile, median, upper quartile, and maximum, as well as the mean and standard deviation. Below is the box and whiskers plot that is constructed from a 5-number summary. From the box plot, it can be seen that the median of high cholesterol is higher as compared to the median of normal cholesterol. This is the histogram that is constructed from the frequency of the dataset. From the histogram, we can therefore calculate the kurtosis as well as the skewness of the data. For high cholesterol level, there is zero skewness as the shape of the distribution is approximately symmetrical about the middle line and the value is 0.485. It is also zero kurtosis as the value is 0.234. Since the kurtosis is within -1 to 1, therefore we can conclude that our summary statistic is normally distributed, as it matches the Gaussian distribution whereby mean equals to median. Also, the skewness of the data, which is 0.234, indicates that it is within the range of -2 and 2. Therefore, our summary statistic has an approximately symmetrical distribution. For normal cholesterol level, there is zero skewness as the shape of the distribution is approximately symmetrical about the middle line, as the value is 0.320. It is also zero kurtosis as the value is 0.234. Since the kurtosis is within -1 to 1, therefore we can conclude that our summary statistic is normally distributed, as it matches the Gaussian distribution. Also, the skewness of the data, which is 0.234, indicates that it is within the range of -2 and 2. Hence, our summary statistic has an approximately symmetrical distribution. By comparing the median of both data, the median of high cholesterol is 81 as compared to the median of normal cholesterol of 79. For the comparison between the mean of two groups, the mean of high cholesterol is slightly higher than that of normal cholesterol. Therefore, we can conclude that the central population of Singaporeans with high cholesterol level has a relatively high heart rate on average when compared to Singaporeans with normal cholesterol level. The coefficient of variation of Singaporeans with high cholesterol is 17%, which is significantly higher compared to that of Singaporeans with normal cholesterol, 15.76%. This shows that the dispersion of data values and the spread of data from the central value for high cholesterol is much higher than that of Singaporeans with normal cholesterol.
Inference statistics. Our null hypothesis states that the mean heart rate of Singaporeans with high cholesterol level minus the mean heart rate of Singaporeans with normal cholesterol level equals to 0. This means that there is no difference between the mean of two samples. Our alternate hypothesis states that the mean heart rate of Singaporeans with high cholesterol level minus the mean heart rate of Singaporeans with normal cholesterol level does not equal to 0. This means that there is a difference between the mean of the two samples. Type 1 and Type 2 errors. Type 1 error occurs if we reject H null when H null is true. In hypothesis testing, we set a level of significance, alpha, which defines the area of the critical region. To reduce the probability of type 1 error, we should use a 1% level of significance. However, this will increase the probability of committing a type 2 error. For example, when we repeat the calculation of the mean heart rate 100 times using a 5% level of significance, there will be a 5 times on average whereby the calculation will give the wrong conclusion and fall inside the critical region. The null hypothesis is then rejected when it is actually true. Type 2 error occurs if we do not reject H null when H null is false. The probability of committing a type 2 error is beta, which is the area of the normal curve of the alternate hypothesis that falls inside the do not reject H null region. To increase the power of the test, we can increase the level of significance, alpha, sample size, n, or the size of the detectable difference. For example, when we repeat the calculation of the mean heart rate 100 times using a power of 80%, there will be 80 times on average whereby the calculation will give the correct conclusion and reject the null hypothesis. The remaining 20 times will give the wrong conclusion and not reject the null hypothesis. Yes, the consequences of making such errors are severe in our context. This is because we are dealing with actual statistics from patients who are currently undergoing tests for their heart rate and cholesterol level. This will ultimately affect their health condition and lifestyle. Is the data normal? No, the data is not normal because the population standard deviation was not given. Can parametric tests be used? Yes, we can still use our parametric tests as we can do hypothesis testing and estimation through the t-distribution, which does not require the population standard deviation. It uses the sample deviation to estimate the population standard deviation, and through this, we can still use the t-distribution for our data. Hypothesis testing. Putting our hypothesis to the test. Research data set. The number of sample groups we have is 2, and they are both independent. To test whether the variances are unequal or equal, we use the F-test for equality of variances. F-test will be used to find out whether the variances of both populations are equal or unequal. This is to determine which type of distribution the data belongs to, normal or t-distribution. For the F-test, our null hypothesis is that the variance of Singaporeans with high cholesterol level divided by the variance of Singaporeans with normal cholesterol level equals to 1. For our alternate hypothesis, the variance of Singaporeans with high cholesterol level divided by the variance of Singaporeans with normal cholesterol level does not equal to 1. This is a two-tailed test. According to Minitab, our F-crit values are 1.76 and 0.568. Our test statistics are 1.25. The test statistics of 1.25 is between the F-crit values of 0.568 and 1.76. Thus, the null hypothesis is not rejected, and we can use the t-test method for unknown population SD and an equal variance. Since our F-test shows that our variances are equal, we will then move on to the next test, which is the test for equality of means, which is also known as the independent t-test with pool SD. For the t-test for equality of means, our null hypothesis states that the mean heart rate of Singaporeans with high cholesterol level minus the mean heart rate of Singaporeans with normal cholesterol level equals to 0. On the other hand, our alternate hypothesis states that the mean heart rate of Singaporeans with high cholesterol level minus the mean heart rate of Singaporeans with normal cholesterol level does not equal to 0. This means that there is a difference between the mean of the two samples. This is a two-tailed test. According to Minitab, the t-crit values are negative 1.98 and 1.98. Our test statistic is 1.12. Our p-value is 0.134. Since the test statistic of 1.12 is within the t-crit values of negative 1.96 and 1.96, the null hypothesis is not rejected. Therefore, we conclude that the mean heart rate of Singaporeans with high cholesterol level and the mean heart rate of Singaporeans with normal cholesterol level do not have a difference at 5% significance. We could increase the power of our test by reducing the confidence of our test. However, this would be at the expense of an increased rate of committing a type 1 error in our experiment. Therefore, a larger sample size would be taken to improve on the power of our test without jeopardizing the confidence of our experiment. Is our inference statistics conclusion valid or invalid? The conclusion is valid since we used inferential statistics where we conducted a statistical test such as independent t-test to determine whether the means of the two samples are equivalent. Therefore, this is a more accurate claim as compared to what we did in part 1 of our report, where we only inferred from our data. Does this conclusion match our observation in part 1 of the report? The two conclusions do not match each other, as in part 1, we concluded that the two means are not equivalent, whereas as in the part 2 of the report, we came to a conclusion that the two means are equivalent. However, in part 1 of the report, we merely inferred to the diagrams and plots we made with our raw data and used the descriptive statistics such as inferring from box plots to come to the conclusion that the two sample means are not equal. Therefore, the descriptive part of our research was not as convincing as compared to the second part. In conclusion, we need a larger sampling group by increasing our sample group to a much larger figure to make a more valid claim on whether there was actually a cause and effect relationship between cholesterol and heart rate in Singaporeans. The power of the t-test we conducted is 34.23% according to Minitab. Our desired power for this test is 80%. This is chosen because statistical power is the probability of correctly rejecting a false null hypothesis. We want it to be high so that the statistically significant result will most likely to reflect a true significant difference, or to show that a non-significant difference is most likely not significant. Thus, we want the statistical power of an inferential test to be 80% or greater. What is the sample size that will help you achieve the desired power? The sample size that should be used for each group is 317 as seen from Minitab. The current data size of 50 samples for each group is very different from the number of samples needed for a power of 80%. There is a difference of 267 sample data needed for the power of 80% for each group.